Hello students, now in this lecture we will see about the diffusion capacitance. The depletion layer capacitance accounts for most of the junction capacitance when the junction is reverse biased. When the junction is forward biased, there is an addition to a significant contribution to junction capacitance from the rearrangement of minority carrier density, and it is called the diffusion capacitance. When a small AC signal is applied to a junction that is forward biased to a voltage V0 and current density J0, the total voltage and the current are defined by the equations, that is V the function of t, which is equal to V0 plus VL into exponential of j omega t, and j the function of t, which is equal to j naught plus jl into e raised to j omega t. These two equations comprises the equation number 1, where the jl and VL are the small signal amplitudes for the current density and voltages respectively. The electron and hole densities at the depletion region boundary can be obtained by the equation NP is equal to Ni square by Pp into exponential of Qv by Kt, and which is equal to Np naught exponential of Q into V by Kt. This is equation number 2, and Pn is equal to Pn naught exponential of Qv by Kt. So this is equation number 3. By using V0 plus VL into e raised to j omega t instead of V in these equations, then the hole density is given by as the small AC signal component of hole densities is given by when this V is replaced by V0 plus VL e raised to j omega t, which is given by Pn AC, which is a function of x and t, which is equal to Pnl the function of x e raised to j omega t. This is equation number 4, and for VL is less than V0, we obtain Pn is equal to Pn naught exponential of Q into V naught plus VL e raised to j omega t upon kt, or which is nearly equal to Pn naught exponential of q into V naught upon kt plus Pn naught into q into VL upon kt into exponential of q into V naught by kt into e raised to j omega t. So this is next equation number 5. A similar expression is obtained for the electron density. The first term in this equation number 5, this term gives the DC component, and the second term is the small signal AC component at the depletion layer boundary. Substituting Pn in the continuity equation, which is j omega Pn AC, which is equal to minus Pn AC upon tau p plus dp into dou square Pn AC upon dou t square, or this equation again can be rearranged as dou square Pn AC upon dou t square, which is equal to minus Pn upon dp into tau p upon 1 plus j omega tau p, which is equal to 0. So this is equation number 6. So this equation number 6 is identical to the equation which is given by dou square Pn upon dou x square, here also dou x square, minus Pn minus Pn naught upon dp into tau p, which is equal to 0. This is equation number 7. If the carrier lifetime is expressed as tau p star, which is equal to tau p upon 1 plus j omega tau p, then this is equation number 8. If the carrier lifetime is expressed in this term, now as a total current is given by J is equal to Jp plus Jn. Total current J is equal to Jp plus Jn, which is equal to Js into e raised to qv by kt minus 1. So this is equation number 9, where this Js is given by Js is equal to into bracket E dp into Pn naught upon Lp plus E into Dn into Np naught upon Ln, where Lp is the diffusion length of hole and Ln is the diffusion length of electron. So by making the appropriate substitutions, we can obtain the alternating current density Jl, which is given by Jl is equal to Q into VL by KT into bracket Q into dp into Pn naught upon Lp upon under root 1 plus j omega into tau p plus E into Dn into Np naught upon Ln by under root 1 plus j omega tau n into exponential of qv naught by kt. So this is next equation number 10. So this equation number 10 leads to directly the AC admittance, which is given by Y is equal to JL upon VL. So this AC admittance Y is given by JL upon VL, and which is equal to GD plus J omega CD. This is next equation number 11. For relatively low frequencies, that is for omega into tau p as well as omega into tau n is less than 1. For relatively low frequencies, the diffusion conductance GD naught is given by GD naught is equal to Q by KT into Q into dP into Pn naught upon Lp plus Q into Dn into Np naught upon Ln into e raised to qv naught by kt. So this is equation number 12, which has the exactly same obtained by the differentiating equation number 9. So this is the equation number 9, and the low frequency diffusion capacitance is given by CD naught, which is equal to Q by KT into Q into LP into PN naught by 2 plus Q into Ln into NP naught by 2 into e raised to qv naught by kt. This is equation number 13. And the frequency dependence of conductance and capacitance is as shown in this figure. So this insert figure gives the equivalent circuit of PN junction in forward bias. So from figure it is clear that the diffusion capacitance decreases with increase in frequency, and for large frequency CD is approximately omega raised to -1/2. The diffusion capacitance increases with direct current level. For this reason, CD is specially important at low frequencies and under forward bias condition. So with this, I conclude this lecture. Thank you.